Hello, my name is Cole Francis, and this is Physics 2 Modern, lab number 3. So as far as the overview and purpose of this lab go, the purpose is to measure the distance dependence of a magnetic field to a small bar magnet, and then to compare measurements to the distance dependence predicted by the equations for on and off axis magnetic fields derived from the Biot-Savart law. So the materials that were used for this lab were a bar magnet, a smartphone, which the magnetometer had to be located on in order to determine accurate magnetic field measurements, 2 meter sticks, a magnetometer app, and tape to hold down the meter sticks. So as far as the relevant physics principles go for this lab, the first one is the Biot-Savart law, as you can see there, which helps calculate the magnetic field around a dipole bar magnet, and the distance dependence equations, which are derived from each other. You can see here that it relates constants K and N to the magnetic field. Some of the observations that I made while taking measurements for this lab were that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increased, and that also when the magnetometer was far away from the magnet, it measured as a near zero magnetic field in the x direction. So the measurements I made for this lab, you can see here in the Excel spreadsheet, basically some of the takeaways from the measurements were that as the distance increased, the magnetic field in the x direction increased, and you can see on the plot there the graph of the log of the magnetic field versus the log of the distance. And the slope of that line represents the constant n, which is the distance dependence constant, and the y-intercept of that line represents ln of k, which was used later to calculate the magnetic dipole moment. You can also see at the bottom where we measured the magnetic field at a 45-degree angle from the bar magnet, and we came to a final B net average of 4.72279 times 10 to the negative fifth Tesla. So here's the calculations that we made for the lab. So you can see there that from the slope of that line, we determined n to be negative 2.1764, and we then used the distance dependence equations to find the magnetic dipole moment, which came out to be 3.845 times 10 to the negative 3 angstroms per meter squared. And as for a comparison between the measured values of the magnetic field 45 degrees from the bar magnet, the measured value was much larger than the computed value that I computed using GlowScript. So here you can see the code that I used for the computational model. I basically created a function that found that magnetic dipole B, and then applied that at a bunch of different observation locations to create arrows that represented the field at all those locations. So you can see here the field, the orange arrows are the field at locations parallel to the bar magnet. The blue field is the field, or the blue arrows are the field perpendicular to the bar magnet, and that pink arrow in the top right corner was the field at the 45-degree angle from the bar magnet. And you can see here that the computational model, the magnetic field from the computational model at 45 degrees from the bar magnet came out to be 2.75508 times 10 to the negative 8th. As for the final questions for this lab, if I had not oriented to compensate for the magnetic north, the magnetic field in the x direction would not have been zero due to interference from Earth's magnetic field. And if I were to stick 2 identical bar magnets end to end and rerun the experiment, the value of the magnetic field would be increased in the original setup as the magnetic fields from each of the 2 magnets would add together, creating an overall larger magnetic field. Thank you for watching this lab, and I hope you learn more.